Good afternoon. So, so this week we're covering different algorithmic techniques. And I want to just make it clear that these are not specific algorithms per se. They are categories of algorithms, if you wish to call it. Think of it that way. So yesterday we looked at what I call repeated doubling or repeated squaring, and I tried to describe to you how the idea of the repeated doubling you could use in the context of taking powers, and then you could actually use that with any operation that's associative. So in fact, something like repeated function, you know what iterated functions, you know, remember in CSEC when you might have learned about a function, you learned what, when you compose a function on itself, that we call F2. So F is a function, F of F is F2, and F of F2 would be F3. It's not a cube, but you write it like it's a power. That's an example of an associative combination that you could use the technique of repeated doubling or repeated squaring to solve more efficiently if you have a representation for F composed on itself quickly. So that's just an example. So now today we're looking at a different technique. It's called dynamic programming. And as I mentioned yesterday, dynamic programming is not an algorithm. It's a strategy. And it really speaks to tabulating results to save effort. So I'm going to illustrate that first with the Fibonacci sequence, because that's a real simple example. The danger with the Fibonacci sequence example, though, is that it's so simple, you might miss some important points. So then I'm going to describe to you a different problem called the coin change problem, which is a little more complicated to think about. But when you see how you solve it using dynamic programming, I hope you then appreciate what dynamic programming actually does for you. So the takeaway I want to learn, so essentially it's about tabulating results. It's about tabulating intermediate results that need to get reused again. And what I'm going to try to do is illustrate to you why it's beneficial. And so your takeaway should be, when you're solving these problems, especially if you have a kind of recursive problem, one that has dependencies on sub-problems. If you find that there are lots of sub-problems that are repeated, then that should be an indicator to you, hey, maybe I should be thinking about using dynamic programming. So without further ado, let's illustrate this with our Fibonacci sequence. You know that that sequence, well, in our case, we're going to start with 0. Just because I'll make that be the index. And in general, the ith term, well, it's 0 if I equals 0, 1 if I equal 1. Those are base cases. And then it's the sum of the previous two, right? Everybody knows that, right? Seen that before? Question? Thanks for reminding me. I'll try. Can you see there? Can't? So, okay. The point of the camera was hopefully that you could see there, easier than there. Is there a way to zoom in? Didn't turn it off. Wrong way. All right, keep trying until you go off. Okay, I'll try and write a little bigger. Okay, so So if I had to write a function to give me the ith term of a Fibonacci sequence, or let me say the nth term of a Fibonacci sequence, the natural way you might define this I'll just make this into two cases by saying if it's less than or equal to 1. Oh no, well, fine. That makes sense? So that's the natural implementation of that definition for the recurrence, yes? Okay. Now, given all that knowledge you have now about how to analyze algorithms, anybody have a good sense of what the time complexity of something like this might be like, roughly? Feels like 2 to the n? Worst case, 2 to the n, right? Worst case, 2 to the n. It may not be exactly 2 to the n. But how do you get it? That's an excellent, if your intuition is telling you that, that's excellent. If you actually worked it out, that's even better. Of course, if you worked it out, you would not have quite gotten exactly 2 to the n. Upper bound 2 to the n, yes. But actual value, you'll see that it's not exactly 2. Let's understand why though. What would tell you it should be 2 to something? So you have these 2 recursive calls. That means if you're going to do a recursion tree, the T of n node, for example, is going to have 2 children, T of n minus 1, T of n minus 2, right? And so each child now will have 2 children subsequently. And how high is that tree? What's the height of that tree? Well, by the time you get all the way down to a base case, n would have had to diminish. In this case, it's diminishing only by 1 each time. So it's slowly diminishing. And you would have had to have, the tree is going to have a height that depends on how many iterations you needed for n to eventually diminish to the base case. So that's going to be proportional to n. The problem with that analysis, so upper bound, if I wanted to know worst case, that's perfectly sound because this side is not diminishing quite as slowly. So it's not going to be exact. It's not 2 fib of n minus 1. One is n minus 1, the other one is n minus 2. So your recursion tree and of course in this case, the overhead, of course, each time is going to be point of this is not to necessarily draw that tree and do an analysis on it. It's to point out that the eventual length of my tree is going to be much higher on the left side than on the right side. Because this one is decreasing by 2 at a time. So over here, I'll have T of n minus 4. And way over here, I only have T of n minus 2. Agreed? Okay. So yes, you're right that T of n is upper bounded by 2 to the n. Can anybody tell me what it is lower bounded by using a similar kind of reasoning? Point what? 1.5 to the n. 1.5 to the n. How do you get 1.5?
Because of the feedback constant. minus instead of minus 1. Okay, just max.
Yeah, so if it, no, but that's the wrong maths. So, if it decreasing by, yes, by 2 to the n over 2. So actually 1.414 to the n. Right. So why? Where did I get that from? Because this side is a short side. And it has a height that is going to be approximately half n. If you're decreasing by 2 each time, the number of nodes on this side that you have to, how many times can I decrease n by 2 before I get to something less than or equal to 1? It's about half n. So this height here on this side is the short side, is half n, right? And what you're saying there is that the total amount of work is definitely at least 2 raised to that power, because for every node on this side, there is a sibling on the left, right? So we definitely know that there's at least 2 raised to the n over 2 nodes in total, each carrying an overhead of 4. But this point, the point here is that this 2 to the half is really square root of 2. So this is the same as square root of 2 to So I'm going to draw a different tree because it has a similar structure.
Hello, sir.
There's a computation get done again. So
Hello, sir.
yeah, question?
The audio is dropping in the call.
Volume is dropping in the call.
Audio.
Audio. Is it okay now?
It seems like it, but every 2 to 5 minutes it's dropping out.
All right, wait. It might be the. I'll leave the meeting and rejoin and see if that helps.
Okay, we would have missed everything in the 4th column.
Okay.
Yeah.
Gosh, didn't respond. He's
only your containers. Huh? That's not like mistakes. I was speaking it down.
You defensive.
Graph? Here?
Yes, I can hand out, sir.
I'm about to draw the call graph. Yeah, I'm trying. So, he knows that this is bigger than that? Or not? I thought it was. I'm trying. All right, so I have to remember to draw the letter. All right. But if I keep going to n minus 1, it depends on fib of n minus 2 and fib of n minus 3. Agreed? Likewise, fib of n minus 2 depends on fib of n minus 3 and fib of n minus 4. No. If I mean, of course, these don't necessarily terminate here, but it depends on n. I mean, if n is something like 10, n minus 3 is only 7, so you still have more steps to generate the order. We have more calls under each of these. And if I were just to examine what the arguments look like, n minus 3 here, n minus 4, n minus 4, n minus 5. Okay, and then n minus 5, n minus 6. All right. So the key thing here is notice that you might have seen, excuse me, fib of n minus 3 twice and thinking, oh, that's just a little bit excessive. But it's actually really bad because look, fib of n minus 3 was needed here, was needed here, was needed here. And every time you need fib of n minus 3, it's not as if you use the answer you already computed. You go ahead and compute it, and you have an answer to return to, in this case, fib of n minus 2. By the time we are over here trying to compute this value, fib of n minus 3, that answer wasn't made available. We pretend as if we don't know what it is. And so go ahead, and that fib of n minus 3 needs to make all these calls. Remember, every node in this tree is a separate call to the function. So it's representative of the recursion tree because it kind of tells you how much work is being done. That number there is how much work is being done per call. But I'm trying to focus on what the argument sizes are, right? And that's what I'm trying. That's why I'm illustrating the call graph here. Because if you just look at number of calls in and of itself, you can see that, okay, first you can see the exponential. But importantly, you can see what the computations are. So how do we solve it? Or, well, how do we improve on this? The first time we calculate one of these values, save it. Put it in a table. And then the next time you need to get that value, what you do is check the table. Right? Now, there are two ways you could do this. One is called a memoized computation. So you memorize the recursive call. Memorize, not memorize. That's right. Yes. What password? You mean no amount are you subtracting from n? Seven, 4, and 5. That is correct. 7, 4, 5. 5 and 6 show up in the same level.
Peace.
Thanks for that.
Type something. Type it's better now. You don't have to,
I'm getting a lot of noise from somewhere. All right. I didn't hear the question. Still not hearing the question. I don't even know who's speaking to me. What do you say? Oh, you can save the outcomes of previous calls for future use. And it's called memorization. All right. Now I could do this in one or two ways. As I said, if I use this approach, I could implicitly build a cache, some sort of table or a dictionary in Python, and store the previous values in my cache, and then check if I already have it before I proceed with this code. Okay, so I'd probably do something like this. I might change my code to look. I'll take a cache as an argument. And the very first thing I'll do is check if n is in the cache, return the saved value. And then if not, then I'll just proceed to compute this code. But the key thing is that instead of doing a return, the first thing I do is save it in the cache. So like this. So it's the same code, but here I'm going to save it first. And then I'm going to return it. In this case, I'm assuming it's a dictionary implementation. Yes, let's leave it there. Cache is just a variable name. It will be implemented as a dictionary. I deliberately left the code that I had up so you could see the relationship between the code I'm developing and the code we had before. So here I need to return that sum. What I might do is save it. Got that? If I had a bigger board, I wouldn't have had to erase it. You could have made a comparison. You can see that in this approach, if you can write the code recursively, you can do it with this memoized approach with a fairly minimal change, right? And this is going to work out okay because in this case, it's simple enough that the set of values that I'm trying to save are entirely dependent on the values I've seen. There's only one parameter, one number. And so whatever samples I got in the past, I'm saving them. I know why is it worthwhile to save? Because of what are called overlapping computation. Yes. Well, let me just finish explaining what an overlapping computation. When I say overlapping, I mean the fact that I needed the same computation over and over. So like in n-4, for example, I needed 1, 2, 3, 4 already. Can you imagine what n-100 is? So if you ask for the fib of 1,000, for example, n-100 is, I need lots of those. So rather than compute each of those all those many times, you're computing them only once, and every subsequent time you're going to be able to access it from the cache. The reason why it wins is because of those overlapping computations. If your computation doesn't have much overlap, if every sub-computation is different, caching not going to help you. Question?
So in the result column, will you pass cache MS1?
Yes. Sorry. So you notice that I kind of I forgot the cache reference. So here's what I normally do, and this is just a matter of practice. What I would normally do is set this to default. I make this be a optional argument. So I'll have a cache equal, maybe if it's by default an empty dictionary, but that's actually not really what you want. I mean cache equal cache is what I'll do. And then external, I'll declare a global cache. And it's important that that cache that you declare that's changing is external to this function. That's actually really, really important. Okay? Now, anyway, to be correct, you're right, I should have passed it here, and I should have passed it here. Sorry about that. So this is plus fib n minus 2 in cache. Yes? Yes, absolutely necessary. Question was, is it really necessary to do this cache n equal n? 100%. What's the alternative? Exactly, it's just going to be only 0 or 1, so this is only going to happen twice. Because subsequent times you're going to hit it here. All right, that's another way. Question up front was, wouldn't it just make sense to just initialize the cache in the first place with just 0 and 1 at position 0 and 1? Yeah, you could do that as well. That would work. All that does potentially is eliminate this from your code. But notice what you've done now. It will still be right. But if somebody's reading this, they're like, wait a minute, you forgot the base cases. And it's not really that you forgot the base cases, it's the way you initialize the cache is taking care of the base cases. So overall, it's right, but readability sometimes is an important consideration too when you're developing code, especially in teams. But yeah, functionally, those are equivalent. All right, so that's one approach. Another approach is you could build a table. Just straight up, build a table. Forget the recursive approach. You're gonna build a table, but in the table, you will see the recursive references, because you'll, instead of making a call, you'll actually just be referencing the table. You can see it in this code actually, in a way, because if you notice, every subsequent call, like for example, if I'm doing fibben and I've now called fibben minus 1, eventually something gets stored in the cache when I get to the bottom. And it's gonna come back up and then try and do the right side. Of course, by the time I get to the right side, look at this. By the time I get to the right side here, you see that fibben minus 2 is already done, right? So then technically it's actually going down this chain. And because at that point I'm gonna get real values here concretely. And as I'm returning, I end up, when I do the call on the right side, I immediately get a cache hit, and then I have an answer. And so I never ever actually do the right sides of this tree. And so the overall computation ends up looking like a call here, you know, so I have all these calls, and I'll come back, I'll do one node on the right side, get an answer immediately, come back, pop up, one on the right, pop up. So I never do the whole tree. Even when I finally get to the fibben, it's gonna be, go here and call fibben minus 2, but that's gonna be a cache hit. So it doesn't do all of this underneath it, immediately returns the answer. So the one optimization, one extra step on that we can do is, since I can see already that I'm going to end up having those values before, why bother to make a call in the first place? Just access the table. So once you start seeing that, then you're like, well, why even bother with recursion? In this context, because the problems are overlapping, you could just build a table. So I want to do this Pythonically. All right, so I need to initialize this with my base cases. And the idea is that the table is my cache essentially, right? But what I'm gonna do now is I'm gonna loop until I get to n. And if I don't have, if the length of my table is not yet n, that means I don't know the answer yet. So the length of the table just tells me which ones I know, right? All right, so this is, you could do this half a dozen ways. You don't need to think of the way I'm writing it as the way to do it. There's nothing particularly virtuous about what I'm about to write. So I guess I could say for I'm gonna actually say while. I could do 4, but which one do I want to say? Length table less than? I want to. So while it's less than, I need to keep going. No, less than or equal to. All right. So what am I going to do? Otherwise, I'm going to append maybe I shouldn't have done it this way. Now I'm feeling bad. What? Because I didn't show any of the indexes. And anyway, you good with that? I ended up doing I did something that's very Pythonic. But there's a little bit of a lesson that I was hoping to have brought out that didn't come out after, because the indexes are hidden. And I wanted to show you that. Look, you see? Okay, so all the way, if you're coding in something like C or Java, where you can't normally do this. What does this do? This index is the last element, right? And this is the second to last element. So you're adding the 2 previous elements to produce the next one, which is what you're appending. Right? And that makes sense. That's exactly what you're supposed to be doing. Right? So it's add the previous one and the one before that to give me the next one. So I'm appending it. What I would have done if I were working in a language like C or Java, where the indexes are explicit and that's the only way to access the array, you can't iterate over the, well, not true. If you have an array list, you can iterate over the values. If you have a vector in C++, you can iterate over the values. But that's a kind of new phenomenon. The original classic way is you iterate over the indexes and then index the array. And what you'd have seen is we would have probably allocated the table out to have enough slots. And then we would have had a loop with an index variable counting up to n or n plus 1, whichever. And then we would have said something that looks like table square bracket I equals table square bracket I minus 1 plus table square bracket I minus 2. Right? That was the particular feature I wanted to show you because it would have looked just like, wait, we're gone. Oh, right there. So the recursive call reference to different indexes would have shown up as table references. So what before in the recursive implementation were recursive calls turn into accesses to the table. Okay? And that's kind of a characteristic feature of this dynamic programming idea. Where yes, it's this computation, yes, it is technically recursive in that it's broken down problem into multiple subproblems. But typically when it goes to the implementation of it, you also then figure out, hey, you know, these values up here depend on these low values. So I'm going to compute the independent values first. And so the idea, one feature of the dynamic programming is to figure out which order you need the results so that at the time you need a result, all the things it depends on are already available. Okay? And so typically when you look at implementations, they don't look anything like a recursive function. They end up looking like these iterative implementations. But when you look at what is happening in the table, that is really kind of like a pseudo-recursive call, exactly, because you're referencing a past value. Okay? And that's the concept. Basically, memorize, tabulate, and determine what order you need to compute the values. You always try and compute, make sure that when you get to the point where you need a value, everything it depends on is already pre-computed. That's the key. Any questions? All right. So let us talk a little bit about this classic problem called coin change. Anybody heard of the coin change problem? Oh, great. Okay. So what I'm telling you is new to you. All right. So here's what we want to do. If I want to know how many ways, let's say I have, let's see, what coins do we have in Jamaica here? Still use $1?
Yes, sir.
Okay. Well, that's it. Okay, I don't want to make it too many. Well, 1, 5, 10, and $20. Right. We used to have 50 cents, but that's true. All right. So not the money that the beggars on the street. If you give them the red money, they say no, don't bother with that. You can keep that, right? So if you have, I don't give them red money, but if they beg me for something and I show them in the car, like I only have red money, it's like, all right. You can keep that, exactly. That's just gonna wait down their pocket. Then they don't have time and space for that. Right? But let's say I'm focusing only on the 1, the 5, the 10, and the 20. I don't like those, but anyway, all right. I'm actually, for my example, I'm gonna make it smaller because of how it works. But you have a certain set of coins with given denominations. And the question is, for a given amount of money, how many ways are there to make change in the denominations that you have? So let's keep this simpler. Suppose I had a $1, a $2, and a $5 coin only. And I wanted to try and make change for $10. How many ways are there of doing that? That's what the question is asking. So for example, I could give out all 10 ones. That's one way. I could give out 2 5s. I could give out 5 2s. I could give out 5 1s and a 5. 8 1s and a 2. You get the idea. You're trying to count that. Count the total number of ways you can do that. So the question is, how would you do that? Still? Maybe that message old, huh? Yeah, but it needs a timestamp. So anyway, I'll continue to try to write bigger. All right. The coin change. Yeah, I suspect so. That's a statement to the problem. So any thoughts on how to do it? Got a moment to think about it?
Try to squeeze it with the smallest amount of denominations. So like if you have 10, you get the smallest is in 5 and 5.
Oh, fewest number of coins. And then what?
And then by the amount of it, then you use the lesser denomination to 5. And so on until you reach the smallest denominator.
Okay. Can you think of a recurrence? Can you think of a way to represent this problem in terms of itself with smaller inputs? Base cases?
Excuse me, please, sir.
The amount of money is N.
Hey.
Hang on a minute, please.
Yeah.
So yeah, okay. So if N is bigger than the largest denomination, you think? All right. So I'm asking for an approach to try and solve this. And one suggestion up front was start with figuring out what the base cases are. And that's definitely needed. So it's not about, I mean, it's actually up to you how you want to proceed. I think the important thing though is to understand try and define a function or a notion of what will give you the answer. And then if you can represent that in terms of smaller input sizes, smaller arguments. All right, I'm coming back. Question, suggestion? So what we need is a statement of what must be true. And so that we can then go ahead and try and implement it as code. Cave Hill, you had us input? Crickets? All right, so let's start by defining a function to represent that number. So suppose we say let C of n comma d.
So yes, sir. Sorry about that. We were inquiring if you would be able to read off what you just wrote on the board, as the right-hand side of it is hard to see.
Cameraman, is it possible for you to maybe hold it just so that they can read it? They're trying to read this. It says, given a set of denominations D and an amount of money N, determine the number of ways that change can be made for N using coins only from D. All right, so
what's that in brackets? Answer only?
That's not brackets, that's coins from D. Coins only from D.
Okay, thank you.
Yeah. All right, so let's see of Dn represent the number of ways to make change for n from D. All right, so here's the insight, the key insight. For each denomination, I can ask, am I going to use it at all or not? So let's say with the example I was giving you, if it was 1, 2, and 5, I can decide, am I going to use the $5 at all or not at all? Agree? Right, so now those two, if it's suppose I could, by magic, get the total number of ways that I could make change without using the $5 bill at all, $5 coin. And then I found also the number of ways that I could use with using the $5 coin. Do you agree that the total number of ways must then be the sum of those two? Because those two are mutually exclusive. Either I'm using the $5 or I'm not. Agreed? Now, here's the other observation to make. If I'm using the $5 coin to make N dollars, would you agree that the total number of ways of being able to do that must be the same as using the same set, but to make N minus $5? I never say that again. So D is some set, let's say 1, 2, 5, and I have N dollars to make. And if now I'm trying to count how many ways I can make N dollars using all of those three, and I'm gonna use the $5. Do you agree that then I could say, well, if I'm gonna use the 5, then that means I have to take 1 5, that have N minus 5 left to make. I've already decided to use the 5. So if you knew the answer to how many ways you could make change for N minus $5 using the same set that I'm working with now, that would tell me the same answer as the number of ways to make change for N dollars using the same set of now, assuming I'm using that $5. Yes? All right. So let's say that that's a particular coin. That might be the $5. The number of ways to make change from D, the set D for N dollars, is going to be the sum of, so now I'm saying either I choose not to use that denomination, and I need to make the same amount of money using the other coins. Or I am using it, but then I'm going to count the number of ways using the same set, N minus DI. What? What's what? Second to last line, what's what? Oh, here, comma N. Yeah, that's D without DI, comma N. D minus DI in a set. So you can set that coin out, but it's the same amount of money. And here you're using the same, you are using the denomination, but then it'll be the same as the amount of money less that denomination. Now I'm out of time, so I'm not going to be able to show you the full story, but what I'll try to do, let's use with a specific example. Let's keep this relatively small. What I'm saying is, notice that when we had 1, 2, 5, that's my set. I'm going to use angle brackets because they're faster to write. And 7, according to this idea here. Let's say I'm saying, suppose I don't work with a 1, or I do work with a 1. So this one is, I'm not working with the 1, and this one is, I am working with the 1. So if I'm not working with the 1, then that means I'm only working with the 2 and the 5, and I still have to make change for $7 because I've decided not to use the $1. But if I decide I am using the $1, then I need to now make and it's the same as finding it out for 6. Why? Because if I chose to use the $1, that means I take at least $1. But I had 7 to start with, so I have 6 more left to make change for after I take that 1, right? So therefore, this is saying if you knew that number is exactly the number of ways you could have made change for the $7 because you've already taken $1 here. Got that? That's what that essentially represents. So at this point, I've made progress by taking $1. And here I've refused the $1, so I still have $7 to make change for. Now what you can see is I could keep going. And what's going to happen over here, I'm going to end up with, well, do I want to work with the 2? If I'm saying I'm not working with the 2, if I say I am working with the 2, all right, now you can keep going. And I'm going to stop here because I want the time. But the small issue that I was going to point out to you is that if you take the normal simple caching approach with this, you discover you run into problems. And the problems are that what you're going to index the cache with. Because you have to capture the input size. What would constitute an exact same input? There's no debate that you will see repetitions. Because, for example, you know, the ways of doing 5 using 2 and 5 will come up again after we deal with 6. If I took the $1 and decided that, yeah, and then try to find out how many ways that they're making the 5. With the 1, 2, 5, I'm going to end up seeing this one as a sub-computation, sub-problem. So there are lots of overlapping problems here. So I will get them, but the problem is, how do I key them? How do I know when I've seen one before? If I try and store the whole set, the problem is I'm going to need the power set of, because that's all the set of possibilities of subsets. If I'm going to try and index it, and that's going to explode exponentially. So there's a slightly better way. I'll leave you to look it up. Because it was meant only as an illustrative example. If you want to see the solution, I can show it to you on Friday. But you want to see it on Friday? All right, I'll pick it up on Friday and show you. I can't see the board? Where's? Huh?
Sir. Sir.
I'm gonna try and help you out. Yeah. Come along. Can you see now?
Sir, can you hear me?
Yeah, I'm asking if you can see now.
Yes, sir, but on and on, this is becoming a recurrent issue. Several times, right, we are not able to see. This is not conducive to learning on anybody on the online sense. It's only for the students who are there live.
Yes, I agree. The infrastructure has not been set up properly for this. And it's a complaint that's been going on since inception. I don't know what else to do for you guys. But I have reported this at every level that I can. I recommend you do the same.